Okay, so today we have this claim which says the sum of I squared as I goes from 0 to n is equal to n times n plus 1 times 2n plus 1 all over 6. And we're asked to prove this claim by induction. So the first thing we're going to do is the base case, prove it for the base case, which is n equals 0. So base case n equals 0. Well, so if n equals 0, we're doing this, the sum of I squared from I equals 0 to 0. And this is one of the properties that we already know, which is that if the first and last number of the summation are the same, then we just do the summation is just equal to that the expression of that number. So that means that here, since we're starting at 0 and we're ending at 0, then this is just equal to 0 squared, which is 0. And we have to prove that this claim right here that we have, this expression, holds for 0. So let's just substitute 0 into that expression. So let's see if it equals to it. So this is 0, 0 plus 1, 2 times 0 plus 1 over 6. And we see that everything is multiplied by 0 right here. So obviously this is also equal to 0. And this is very good because that means we're done with the base case. We've just shown that the expression we're given, n times n plus 1 times 2n plus 1 all over 6, gives the same result as the sum in the summation of I squared from 0 to 0. So expression holds for n equals 0. Okay, so now we can move on to our induction hypothesis. So I'm just going to write IH for short for induction hypothesis. And that's going to be, we're going to say assume the expression holds for n equals k. So we're going to say assume that the summation of I squared from I equals 0 to k equals to, and instead of n in our original expression, we're going to write k. So this is just going to be k times k plus 1 times 2k plus 1 all over 6. And the condition is for k is bigger or equal to 0, which is the same as saying, well, this is the same as saying, I'm just going to write in brackets, k is an element of natural numbers. So now we have our induction hypothesis and we can move on to our step, inductive step. So just step. So we're going to prove this. We're going to assume that this holds for k. So now we have to prove it that it also holds for n equals to k plus 1. So when n equals to k plus 1, then we're going to write the expression. So we're doing the summation of I squared from I equals 0 to k plus 1. Okay, so we want to prove that this expression also holds for k plus 1. And we have a summation here. And what we can do is split this summation this summation expression. So we're going to split it into the sum of I squared, I equals to 0 to k plus k plus 1 squared. And this is just using the simple rules of summation. And why do we do this? Well, we can see that this allows us to use our induction hypothesis. As you can see right here, what we have is we assume that this expression equals to this right here, which is good because now we can say, well, let me just scroll down a bit. We can say this is equal to, and I'm just going to write IH over the equal sign, which means by induction hypothesis. This is just stating that we're using the induction hypothesis. So this is equal to, well, instead of this sigma notation, we're going to write the expression we had above, which is k k plus 1, 2k plus 1 over 6, and the rest doesn't change, so this is k plus 1. Okay, and before we continue solving the question, it's good to always write down what you're trying to achieve. So in this case, by manipulating these two expressions, what we want to achieve is something like, we want to prove that this is equal to something like k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 over 6. And this, if this looks weird, well, that's because just we're trying to prove that this holds for k plus 1, and the only thing we do is substitute k plus 1 into that expression. So that's where we get this expression from. Okay, so now we have our goal. Let me just clarify, this is the goal so we don't get confused. So this is what we're trying to prove. Well, let's see what we can do. Well, we can merge these two into the same fraction by multiplying the k plus 1 squared by 6. So this is going to be 6, and this is going to be k plus 1, 2k plus 1, plus 6, k plus 1 squared. Here we can take k plus 1, a factor of k plus 1 out. So we have 6, k plus 1. So if we take k plus 1 out, we have k times 2k plus 1. And here is just going to be plus 6k plus 1. And we can just do simplification from here. Nothing fancy. So it's just going to be 6k plus 1, 2k squared plus k plus 6k plus 6. And we're, if you've noticed, we're already closer to our goal, because if you notice that we have k plus 1, the term k plus 1 here, and that was part of our goal, so we're getting closer. And here's where you might fall into the trap of oversimplifying. You might be tempted to like add the k to 6k because you just want to simplify. That's how we usually do it. But that would actually not help us get to our goal, because here what we're doing is just manipulate this expression algebraically to get it into a certain form. So maybe oversimplifying is not the way to go. So actually the thing to do here is, which takes quite a bit of time to realize. I myself oversimplified in the beginning and realized that didn't help. So now what we can do is, well, the k plus 1 doesn't change, neither does the denominator, and here 2k squared. So we have 7k in total, and what we can do is, well, that's just equal to 3k plus 4k, which is 7k, and we're just gonna write plus 6. We don't touch the 6. And you'll see why this helps us achieve our goal. Well, because now what we can do is, we can say that k plus 1, and what we can do is group these two, the 2k squared and the 4k together, and we can group the 3k and the 6 together, and we will have two different terms when we do that. So if we take the 2k squared and 4k and we take the factor of 2k out, we're going to be left with 2k. This is just going to be k plus 2, and then plus 3k plus 6 over 6. And now we do the same with the 3k plus 6. We just take the factor of 3 out. So this is 6, so it's k plus 1, 2k, k plus 2, plus 3, k plus 2. And now what we can do is simply just take the factor of k plus 2 out, and that would just mean that we will have 6 k plus 1 or we take the factor k plus 2 out, so k plus 2. And what we have left is 2k plus 3. And again, we're already closer to our goal because if you notice again, I'm just going to highlight it. K plus 2 is the same as k plus 1 plus 1. So the way we wrote why we wrote it as k plus 1 plus 1 is to notice that we're just substituting k by k plus 1. So that's good. We also have our second term. So I'm just going to rewrite this so you can notice. This is k plus 1. So it's easier for us to notice. This is k plus 1 plus 1. And now, for the final term, we want something in the form of 2k plus 1 plus 1. And as you can see, well, we can easily do that because what we have is, well, I'm just going to write it 2k plus 3, and this is equal to 2k plus 2 plus 1. And as you notice, if we take 2 out, then this is going to be 2k plus 1 plus 1. And we have what we were looking for. So that's great. So instead of 2k plus 3, we're just going to write 2 times k plus 1 plus 1 and all over 6. And this is perfect because we are done. What our goal was to prove that this was our goal. We were trying to reach this expression, and we have exactly derived that expression. So that means that the summation is equal to this. So the claim holds for k plus 1. So we're going to just write a mini summary for our inductive step. So the claim holds for n equals to k plus 1. And we're basically done. We just need to write a conclusion. If you're just doing this for fun, you don't need to write a conclusion, but if this is for an exam, then it would be good to, you kind of need to write a conclusion because then you might lose some marks. And the conclusion is easy. We say, well, just a conclusion. And it's a good idea just to keep our conclusion nice and simple and concise. So we're going to say, we have shown the claim holds for n equals 0. Also, if we assume that it holds for n equals to k, then we showed that it also holds for n equals to k plus 1. So, and now the last sentence is just going to be, this means the claim holds for all natural numbers n. And that's our proof. Hope this video was helpful, and thank you for watching.